Good afternoon. This is the exploit track, and this is our final talk from Tim Shelton. Without any further ado, I present you.
All right. Great. So for you, those of you that are not here live, we've actually got more people. I was just informed we got more people on the internet watching me than we do here in the room. So we can pretty much hear a penny drop. So my name's Tim Shelton. If you can't tell, I'm from Texas, and I am not a steer. So you can figure all that out. Just kidding. I'm with a company called Hawk Network Defense. They're a security information and event manager. Basically, we created a product in 2006. I helped create algorithms and all that jazz, and so we're competing in that market. Let's see. One of the key things we do have is we have a real-time I-Series agent. Anybody run the I-Series AS400 out there? Yeah, I got 4 hands. That's awesome. All right. So I know the rest of you are lying because I know everybody has an I-Series. So a little bit about me. Back in 2005, I was so let me back up. I'm pretty sure you never heard of me, so that's why I put the slide in there. Back in 2005, I was one of the first people to break out of virtualization. I broke out of VMware, compromised the VMNAT daemon through a funny FTP request that ended up being heap corruption, and so ironically, heap corruption, and ended up compromising the host operating system. What that did was created a large security market around virtualization. Had I known that was going to be so popular, I might not be standing here today talking about this and other things. So I definitely missed that boat, even though I kind of kicked it off. So I've been involved in countless Microsoft, Adobe, Apple bugs, vulnerabilities, and/or exploits. I'm with a group called Black Security. Also, my name is Red Sand. In fact, if you don't know who I am yet, does anybody remember Stroke dying this year? Anyone? I'm the guy that killed Stroke. So that was my blog post at midnight that we thought was a good idea, and it just it got a lot of momentum. And so who knew, right? Who knew? I was also involved with the releasing the first universal exploit for the 2009 Adobe JBig2 bug with a co-schemer of mine, Russell Sanford, also Exort. He's with Black Security. So we're going to talk about the importance of IBM AIX, kind of where it came from, how IBM views it, how the rest of the world views it. I'd like to get some feedback on how you guys view it also. I've gotten tons of different feedback when I've been here at this conference, so I'm kind of curious. And then we're actually going to go into the different types of methodologies. So we're going to cover 2 methodologies today. One, and we'll get into that in further detail, but one is required in one situation, and then in another situation, another one's required. So we kind of killed the entire broad spectrum and made sure that we got everything covered. Oh, and we'll have a live demo, which is actually a lie because I pre-recorded it because I went to a talk yesterday where their demo didn't work until the 3rd run, and nobody ever likes a failed demo, so. All right, so IBM's view of AIX. This is taken from their marketing information, actually on their website, the front page for AIX. I feel like I've highlighted the cool part. The cool part being they feel it's very secure. You'll see that part of it is, they feel that IT needs to provide rock solid security and other stuff. And that's why we feel everyone is choosing AIX to run all of their systems on, all of their infrastructure on. So we're going to kind of cover that a little more too and show you where AIX is as far as the progression of making sure they're securing their stuff in comparison to other operating systems like Windows or Linux or even Mac. Or even Solaris, actually, now that I think about it. So the question is, why do we use AIX? I know personally I use it to hunt for bugs, but the rest of the world uses it for a few reasons. So ERP, Enterprise Resource Planning, which that's a fancy term for data management. Good examples of that, so good example of applications and whatnot that run on AIX would include PeopleSoft, SAP, Oracle, so DB2, and there's probably a slew of others, especially in the telephone world, the telecom world, the medical, healthcare world, as well as federal, state and local, and foreign governments. I've also found that most of the companies that I see running AIX tend to have been around before the creation of these things we call computers. And it seems like that IBM sold them on, or, so let's back up. IBM obviously, is one of the reasons why we're here, because they created x86 and they released it, and then they created a market and so on and so forth. And so because they did that, a lot of people have a lot of faith and take a lot of guidance from IBM. So with that said, ZOS, AIX, and the I series, which used to be called AS400, now it's actually System I, excuse me for any people out there that are waiting for me to correct myself. Those types of systems are really what we see as the predominant systems that run the critical back-end, like mission critical stuff for different companies. It seems like companies, the newer companies today, are all focused on virtualization and are all running x86 or x86-64, and maybe a little bit of Mac thrown in there. But typically, like I said, what I end up seeing is in the environments that do have AIX, they've got at most 5 pieces of hardware, and typically each one of these power machines are probably running between 1 and 5 and sometimes more LPARs, which is their fancy term for basically a virtualized, near virtualized instance of AIX. So typically when I do a pen test and I'm hunting for AIX, so it seems like other people, when they do pen tests, they kind of say, oh, AIX, let's go on the other stuff because I've got 20 Windows boxes that I can own right now with Metasploit. Forget that thing because who uses it anyway? Well, ironically, while there may be a small instance of it, the majority of company data, like the critical data, tends to be in that environment. So like I mentioned earlier, so we talked about DB2 and Oracle and PeopleSoft and JD Edwards and all that. Well, companies rely on that pretty heavily to ensure that as they function as a company, as a business, things work as they need, and this is a type of system that they've had together and in place and been supporting since 1990 or even sooner. So, all right, we're actually going to do a little bit of a review. A great man, David Litchfield, if he's here today, I'd certainly like to meet him. I was told he was here, and I'm sure he's not at my talk because I think I'm the only one here. But oh, sorry, I just derailed myself. Anyway, so back in 2005, David Litchfield decided that he would also focus on AIX, and what he went and did is he documented a methodology of heap exploitation for a specific type of scenario, and we'll talk about that. And what we're going to reference is free/rightmost. So the general summary is the Litchfield methodology allows you to take execution of code, control of the execution of code so allocation, and then there's corruption somewhere, and then a buffer is freed. And then that's an instance where the Litchfield methodology would be used to take control of the code execution. We're going to, once again, go through that a little bit more, but and then we're going to go through my method, which is or the new method, which happens the other way. So Litchfield's research kind of pioneered some of the security focus on AIX. So I mean, this might be a bad reference, but back in the day, everyone said Linux was so secure because nobody looked at it. And I kind of feel like AIX is in that same kind of realm. Everybody claims it's super secure because all these governments are running it and all these huge companies are running it, and oh, by the way, we never hear anything about it, so it's got to be secure, right? Yeah, the answer is no. So we're going to go across and show you exactly where AIX is as far as the operating system and what it does to protect you from not doing all these cool hacker things, whereas Windows and Mac and all these other guys are way down the line with different types of cookies and randomization and things that they're doing. So it still kind of blows my mind sometimes. So Litchfield's research was done on IBM AIX 5.3. I have verified that it does in fact work on 6.1, in case anybody cares, because I guess at that time it didn't exist, so he wasn't able to claim it. But so, David, your stuff still works. Great. What he provided us was a way of achieving a bidirectional double pointer overwrite. And I know that's a fancy Falui term, but what I'm really trying to say is there's 8 bytes. So if it's 32, it's 8 bytes, and then they're getting swapped out in memory. And so if anybody's familiar with heap exploitation in general, the general methodology is a controllable 4-byte or double 4-byte overwrite, and that's been around since, who the heck did the first one? So anyway, it escapes my mind. But so it's been around for a while. It's very well documented. I mean, there's only a few ways of really taking control of code execution. You're either going to overrun a buffer and overwrite something on the stack that's going to get returned into PC or EIP. And then the other way is you're going to be able to write something that you control to a function pointer elsewhere that's not actually a dumb overflow. It's kind of a little bit more sanitized, but not that much, obviously. So, what it takes is about 8 bytes. If I can corrupt 8 bytes on the heap, then we are good. Like, we are golden good. What this allows me to do is, with these 8 bytes, I can point it to other things that I control differently, and we can make all sorts of happy, great things happen. So the first 4 bytes is actually the location of our fake heap frame in memory. And I know I just read that off the slide, but I'll expand a little bit more. So what that means is our only prerequisite is we need to have a piece of memory somewhere that we can stick our own stuff in that we can reference later. So if it's a local bug, people would use the environment variable, environment. Other people might use an argument. Other people might actually take advantage of something in the application itself and utilize that. Typically, it's best to use something on the stack, but you could use something on the heap hoping that the same location is going to be returned to you every time. So for the things that I've done, it's typically, so as far as remote goes, that's a whole other story. Typically, you have to utilize something that the application is doing because there's however else are you going to get it there, right? So with the first 4 bytes, we're going to tell it, hey, by the way, the next location is over here. Well, let me back up. So what we're doing is we're corrupting a double linked list. That's it. That's it, all of it. So the header is a linked list that says, okay, the next guy is over here and my friend on the left is this way. And that's it. So if we can say, no, the next guy is this guy and it's something malicious that I control, then we can take advantage of the allocation algorithms that AIX has provided to take advantage and do the things that we want to do. The last 4 bytes is actually our heap size. So it tells it how big the chunk of memory is there. So the AIX algorithm can actually can monitor that and take advantage of it when allocating heap chunks that are the same size. It likes to keep it in the same area. And that's something that a lot of people do. And I'm sure we can go into further detail. So we have a buffer of 1024 bytes. This buffer is the buffer we can corrupt. And you'll see that just after this buffer is our heap header for the next heap segment. Or the next node in the linked list. So what that allows us to do is, like I mentioned, we're corrupting just 8 bytes, and those 8 bytes is all we need to move things in the other direction. The heap size, so when we're actually corrupting this, heap size doesn't matter. So size doesn't matter. That's what she said. But the only requirement is the heap size needs to match the same heap size in our fake frame. So it's pretty simple, pretty basic. So when we create our fake heap frame in memory, this heap frame, once again, as I mentioned, is responsible for allowing the heap to have a better understanding of what it's doing and control the algorithm in general. Once again, the element is a linked list. Look, I covered a lot of this already. Does require a controllable location of memory, and our fake frame only requires 16 bytes for this method. So in the next one, it's actually even smaller. So with if we can get 16 bytes somewhere, plus shellcode, right, then we can, once again, do the things we want to do and slap AIX around like it doesn't know what it's doing. So the first 4 bytes of our fake frame is going to be a PowerPC branch instruction. So anybody here not familiar with power, RISC architecture or anything like that? I see 0 hands. All right, no, 2, 3, great. 4, all right, 5. What that is, basically, if I can relate it to like an x86 world and then I don't get flamed later, is a call. So you're calling a function, a branch is pretty much the same thing. There is a little bit of differences, and we'll go into that. So the second 4 bytes is required to be a NOP. And I'll go into more detail at the end of the end of this talk, but the reason for that is, so power and RISC and pretty much all the RISC, all the RISC, actually do something called instruction caching. So when you do a branch, it actually executes the next instruction before actually calling and doing and branching out. And so I'm not, let me back up, I am not that smart. I mean, I'm a good old Texan boy that thought we could make this happen. So I can't tell you why that's better, but they think that it makes it faster, and I believe them because I drank the Kool-Aid, I guess. So the third pointer is the pointer to the value we want to overwrite. So this can be a function pointer that points to, so in AIX, the file format's COF or XCOF, and so if you can relate it to L for PE32, there is a list of function pointers that say, oh, by the way, system's over here, and free's here, and malloc here, and string copy's here. We can overwrite this table or hijack one of the functions of the table. So if you can find a function that's called pretty close after we've overwritten this, then instead of going to the real system or the real malloc or what have you, we're actually going to, it's going to execute our pointer, it's going to hit our pointer instead and go to our code. Also, obviously the other way is the good old, overwriting your return stuff on the stack, which typically makes a little bit more sense in some areas. So if you're doing just a demo app, maybe I would either overwrite something on the stack, or I would maybe overwrite exit, because in the end everything exits, and just to kind of give you a good idea of how that works. But in a real life situation, you've got to pick something that's going to happen pretty close and that you can actually leverage pretty well. And so once again, the last 4 bytes is the heap size, and that heap size once again needs to match the size that we already overwrote when we corrupted the data. If we only have 4 bytes of corruption, then we need to make sure that size matches whatever the size is already existing. So you don't have to overwrite the entire thing. You can overwrite just 4 bytes of it, but you've got to make sure that size matches. Otherwise, we're not going to get to a certain area code that I feel it's necessary to leverage and take advantage of code execution. There may be other ways without having to get it to match, but the way that, so Litchfield's methodology as well as the methodology that I'm going to be talking about later, both require it to match. Okay, so a little bit of visualization here. I'm not a big picture guy, but I did create this. It's my pretty picture, and it's probably the best picture I've ever made. Once again, beginning of the frame is our branch instruction. So there's different types of branch instructions. There's conditional branch instructions, and then there's just your basic branch ignorantly and go. One of the things with the ignorant branch instruction is it actually contains a null byte. However, so anybody heard of H.D. Moore? I hear he's popular, but so I was talking with him not too long ago, and I actually found some documentation where he's like, oh, but if you change it to, I think, 0x48, then it still works, and it's kind of undocumented because I haven't found it anywhere in any like PPC documentation, but apparently that it is what it is and it works, and I don't know why, and maybe he does, and maybe he doesn't, I don't know, but it still works on Power 6 and Power 7. So I was kind of surprised to see that was still a useful piece of information. If you don't want to utilize that, and or later on down the road, Power fixes all that, or it's all fixed by IBM for Power, you could use a conditional branch, and you just need to figure out which condition it's going to be. So if you pick the wrong condition, then obviously it's not going to go to it, right? So you got to make sure you have the right environment for that to occur. Next one's a NOP instruction, once again, because of the caching. The third is location of a function pointer, once again. Stack or a function pointer somewhere. You can also maybe abuse another function pointer on the heap. So, I mean, you've seen the talks for heap spraying and some of the nasty stuff done in the corruption, for example, like in Windows applications such as Internet Explorer and things like that, use after free, where you're basically overwriting function pointers that are already existing on the heap. So C++ objects, when you allocate a new C++ object and there's function pointers in there, that's kind of how that's done. And once again, heap size. So please note at the bottom, I did not do this image. This came directly from Litchfield's paper. So David, don't come after me. I'm giving you credit, dude. You'll see that I mentioned the bidirectional double 4-byte overwrite. And I'll kind of explain his image a little better because it kind of looks convoluted, but it makes complete sense to me. So you're seeing that they're being swapped out. So we have both. So this one is a little bit more complicated. So we have both values, but the values also have to be valid memory addresses because they're going to get messed with also. And basically, wherever we're overriding at, they're going to swap that data with the data with our fake heap frame, and we don't care anyway because it's malicious and it's doing what we want to do, and we're not going to reuse that ever again anyway. So, got any questions before I go on? Sweet. All right. So I'm a bad coder. I wrote a really bad function, and this function allocates 20 bytes. And then we copy, and it's uncontrolled, however much data it passes as an argument to this heap segment that we just were given to us by the AIX Heap Manager. And then we free it and then return. So what that does is we have corruption in the middle. You'll see I've highlighted that. And then it's going to be freed. And so what happens is the AIX heap management is going to go, okay, well, let me walk this linked list to the right. I was going left, and that's the wrong way. So it goes down to the right, and as long as the heap size matches the same, it's going to keep walking this list. But as soon as the heap size changes, then it's going to do something else. And like I said, that else, I haven't done too much research on it, but the else might be leverageable in some way, but we're going to focus on leftmost and rightmost. So within leftmost and rightmost, where it's kind of pretty much the same thing, but it's going to allow us to do the 4-byte overwrite. As I mentioned, I do document the correct pointers to hijack, and so I feel like it's necessary to document this a little bit better because this does not apply to the next methodology. This is only for the Litchfield methodology, which, once again, saved linked registers, callable functions in the applications export list, and then function pointers found on the stack or heap. Their function pointers may or may not be common. You just got to have a better idea of what the application is doing and how you can leverage it. And so that's why it takes learning PPC, and you got to reverse engineer and all that. Oh, look. All right, so now we're at the new methodology. So once again, any more questions before I go on? Sweet. All right, I must be talking great. So this next methodology, so in the past when we free a buffer, then it uses the rightmost, and it has to walk this double-linked list that manages the heap elements to the right. When you malloc after corruption, it actually goes left to add it within this double-linked list, so it's all contiguous. Yeah, that's about it. All right, I got nothing. When we're unlinking an entry and linking an entry, we're walking through, and when we see, when the algorithm sees that a size matches and it's at the end of this type of match, then what it's going to do is it's going to insert this element, the new element, into our linked list, and it's going to make sure it's there. And so this is how we're able to take advantage of this. Like I mentioned before, when it may be possible in the other routine, but this is pretty basic. It's your basic 4-byte overwrite, and Once again, I'm lazy, and KISS, keep it simple, stupid. So I just kind of took it and ran with it. So with the new methodology, a lot of it's the same. We do have to have a controllable piece of information, controllable piece of data. So whether it's on the heap or if it's on the stack, or if you find some new location to put it that nobody knows about, awesome, good for you. The only difference is, so in the past when we needed 16 bytes, this one we only need 8 bytes. So an example for like some sort of proprietary protocol where maybe there's 4 or 8 bytes of a reserved something that's not being used, we can maybe pad it there. So example, RPC might be a good example for that. If it's ASCII protocol like FTP, then who cares? You can do whatever the heck you want. But some of the proprietary protocols that AIX likes to really take advantage of and love to death, that's kind of where we're going to start focusing a little bit more. And the reason I feel like it's beneficial for that it's only 8 bytes in this next one is obviously you can sneak this in just a little bit easier and do the things you need to do. So when we overwrite our 8 bytes, which is the same 8 bytes, we're saying 4, but actually no. So this one you have to overwrite 8 bytes. You can't take advantage of the heap size on this one. So the size does matter in this. The first 4 bytes is going to be the same thing. It's the location of our fake heap frame memory. So same location. However, the difference is our heap size is actually the value we're going to overwrite, because what it's doing is it's saying, oh, by the way, this is how big it is. And when we take advantage of that, it allows us to do some pretty funny stuff, and I'll show you a demo here in a bit. So pretty much same slide. I got to use the same image over again, but what I did is actually there's a minute change, and if you can see it, let me know, because I can't see it from here. So same buffer size, 1024 bytes. And then right after this piece of heap element, the next heap frame is going to be adjacent to it. And so if we can overwrite this header, once again, the difference is the function pointer ends up being, or the pointer we want to overwrite is the actual size, but it's size minus 12 bytes. And so if it were 41, 41, 41, 41, you'd have to subtract 12, which I can't do math. I didn't teach that in Texas, so we don't know, but you can figure it out. So when we created our heap frame in memory, once again, it's an element of a linked list. It does require a controllable location of memory. Writing the 8 bytes, writing 8 important bytes, I'm glad I highlighted that, has to contain our unique structure. It's technically the same 16 bytes structure for leftmost and rightmost. However, we only need 8 bytes of it, so we don't care about the last half of it at all. So kind of a little bit of a review. With minimal heap corruption, we're able to take control of exactly what we're trying to do. It is complete code execution, and it does take only minutes to write. So, everybody likes the basic Stack Overflow where you're like, oh, EIP or PC is now my magic number and now I can do anything I want with it. Well, this is pretty much the same thing. The only additional research you've got to do, apart from aligning things, which we'll talk about a little bit more, which is a pain, is also you've got to find the right pointer to overwrite. Once again, so I suggest always start looking at the stack because it tends to make the most sense. Oh, actually, so side note, anybody here heard of ASLR? Address space layout randomization. Yay. Guess what? AIX has never heard of it. And nobody else at IBM, apparently, I mean, I know they have because what's his name from IBM just spoke about all this stuff, but I guess they're on 2 different teams and they need to, cross-educate just a little bit more. So, a part of, one way I might dread giving this talk is now that IBM is very familiar with both methodologies being used, they might decide to fix it one day. So that'll screw up all the fun things I have going for this. So, oh, another thing they've never heard of is heap cookies. Anybody know what a heap cookie is? So what a heap cookie is, when an application starts up, it randomizes a value and it stores this value in memory, and every time it creates a new heap value or a heap element, it'll use this value as a cookie. So when it's going through this leftmost, so if IBM were to fix this, if you're going through the leftmost or rightmost process, you would ensure that this cookie also matches. So the negative part is it makes it a little bit bigger, but the good part of it is you can't just blindly overwrite stuff and then finally come to it. So another funny thing would be is if IBM AIX put the cookie at the end of it, we would all laugh. So the idea is to put it at the very beginning, so that way everybody knows. I kind of made myself laugh there because if they did that, I would seriously lull. Because then you could just do a partial overwrite and go, okay, yay. Another good example of that, so in relation to that, so when they were first messing with stat cookies and they put the stat cookie in between EBP and the return to EIP, so once again going back to x86, you could overwrite EBP and take control that way, and partial overwrites, everybody loves a partial overwrite, you don't have to do the full overwrite, so you can take advantage of the existing stuff. So as I mentioned, our fake frame is a little bit smaller than what we were required in the last methodology. All we need is the location of our shellcode, and the same size has to matter. So location of the function pointer minus 12 bytes. Once again, can't do math, but we'll figure it out, right? So here's a major difference. So I mentioned earlier I felt like it was necessary to document this. One of the differences is while we're able to take advantage of all sorts of fun things involving different pointers all over the place, I found that when we're corrupting it using leftmost, we're corrupting the heap structure, it really does not like that. And if you go just a little bit further, it will really crap out and hate you. So in order to actually take control of code execution and not make it segfault somewhere else where we have to go around and start repairing the heap and things like that, which can be pretty tedious and pain and sometimes non-accomplishable. So the idea is we got to focus on that return pointer on the stack. You know, typically I pick 1 or 2 away from the original function. You can't get it, let it get back to the original malloc, otherwise it's going to go, oh my God, no. So here's a stack trace. So GDB, yay. You'll see that malloc is called. Let me back up. So you'll see the shr.o. So apparently it's shr.c if I had to guess, that controls the heap algorithm. So when malloc's called, malloc actually calls another malloc, which is a generic handler. And then from there, it actually calls something called malloc y, which I don't know what it is, but I can't wait to find out. I actually have done enough reversing on the entire heap algorithm, like our previous speaker, who spent the entire year doing it, and I'm jealous because I wish I had fun things to do like that, and I actually have to do other work for customers. Oh. And then we get to leftmost. And once again, leftmost's responsibility and rightmost's responsibility is to walk this double linked list and find when the heap sizes change, the heap element sizes change, and then it's going to go, okay, let's stick it there. Once again, really bad coder. Me, not everyone else. I'm a really bad coder. And you'll see that I've allocated 20 bytes, and it's going to give me a heap element of 20 bytes. And then what I'm going to do, ignorantly, is I'm going to use string copy, which we've all seen that. And everybody knows not to do that, right? All right. And then we're going to allocate some more memory. And so obviously, because this is kind of fake code, it doesn't really make sense. But in typical environments, I oftentimes see more mallocs occur. Excuse me. I'm sorry. More mallocs occur than in a row than I do malloc in a free that's lined up. They do exist, but I found in my test cases it tends to lean towards using leftmost more versus using rightmost. So when we malloc once again, then it's going to walk it left, and then that's when we're going to use this methodology. So what I feel like I've provided is the all-encompassing way of owning AIX Heap, the Litchfield methodology in 2005 was published, and he conquered half of it. But there's this other section over here, and I've actually in 2006 or 2007, Intrepid, which is with CAU, Maybe you've seen him. He runs around with a green guy named Druid. Anybody seen a green guy? Yeah, we all like the green guy. They found an AIX bug that was set UID something worthless. Actually, it was like set GID something pretty worthless. So they just said, okay, here, forget it. It's not worth anything. So here's how you do it, and then here's all the entire output. And so the reason I know that this exists is because I started Googling leftmost, rightmost, and I found his advisory. But he didn't have any code execution or any any example exploit that showed you actually how to do it. It just showed you how to trigger the bug. So I'm making a huge assumption, but I think either A, he just didn't want to publish, which that's typically not how those guys roll, or B, he just didn't know how, or C, it was worthless once again, and who cares? So it's got to be one of those. So when we're adding an entry, as I mentioned, we were going to go to the furthest heap entry on the left that matches in size, and then we're going to insert this new element in the double linked list. So the heap algorithm needs to know the first entry so it can keep it contiguous and packaged well, and we're not having a bunch of gaping holes in heap, and it can help manage it a little bit better. Oh great, live. So you see I say live demo, but it's in parentheses pre-recorded. There are two reasons. One, like I mentioned, I'm not going to point, sorry. Somebody did a presentation yesterday, and they had some issues with their demo, and that's the last thing that I want. And two, I hear this is called Blackhat, and it doesn't make sense for me to get on any sort of network here, VPN into our own network, which, got to be quite honest, I don't feel like we're as secure as we need to be. And then do a live demo. So it just, part of that gives me the willies. And actually I saw on Twitter earlier that they said, if I hear someone else complain about not wanting to use the network because they feel like they're going to get owned, I'm going to shoot them. Well, I hope you're here at the talk, because you can hit me up later. I know who you are, I don't see you, so. Which, thanks for being a great friend. Okay, so what we're going to do, pause it there. So what we're going to do is I'm basically going to go through of what the example exploit, an example exploit looks like. Our vulnerable function, or I'm sorry, our vulnerable binary is called /leftmost. So this, once again, it's just a basic, generic, let's show you the methodology. This is not a unique bug. All right. We can also ignore the shellcode because, so there's a side note also. I found a lot of the new a lot of the shellcode for AIX doesn't work anymore for whatever reason. So in my research, I've actually had to end up creating my own shellcode that maybe one day I'll create some more and we can give it to HC Morris so they can use it. But right now they're using the same basic 3 different shellcodes that have been published since like 2000 for AIX, and nobody's really messed with it since. And so some of the stuff they're doing doesn't really work anymore. And that's kind of sad. It also tells me that nobody's looking at AIX anymore. So, going back to, I feel like there's people out there that use AIX. Some days I don't feel like I'm getting the affirmation, but I know in the environment that I'm in, that's a true statement. In fact, when I've been talking to people about my talk, so I knew this was going to happen. I knew last day, I'm going to have 8 people in the room. Great. So I've been running around everywhere going, go to my talk. And they're like, well, what's it on? I'm like, well, it's on AIX. I either get the answer, well, who the heck uses that? Or, oh, everybody uses that. That'd be great. And then both those people that have said those things, I see none of them in here. So, oh, yeah, y'all don't count. Y'all don't count. You're my friend, I think, so it doesn't count. All right, so we'll let this run through a little bit. You'll see that a few things that need to be pointed out. Well, first, because this is just an example, what I'm going to do is I'm actually going to run GDB to show you. So I'm not going to just like / and there comes a prompt, because how can you prove that I didn't fake all that anyway? And the entire thing is just supposed to, like the leftmost is actually just a wrapper to like a shell. So, which I can't imagine anybody faking a demo, but I've heard it's happened before. So I want to make sure everybody knows I'm semi-full of stuff, but not completely full, right? Okie doke. So, what we're going to do is, I think it's 20 bytes. We're going to overflow with A's, as you can see here. And we're going to overwrite the next heap element header with, so the variable is called R7, and the reason that is actually R7 is the register that's being used as a reference. So when I'm just going through the stuff, and I found that R7 wasn't used in some of the other areas, so it was just easy to just call it R7, and then that way everybody knows. And then the next is going to be our size. So once again, Litchfield's methodology doesn't require the size to be anything unique. It just has to match. But in this methodology, that is exactly what we're doing to overwrite something. So we need that to be a useful value. I'll let that keep going there. So you'll see I highlight it once again. R7 points to our fake frame in memory, which our fake frame is actually right here. I'm putting it in the environment for this example. And so now that is our function pointer that we want to overwrite that's stored on the stack through our return address, minus 12 bytes. And then our size, so once again, as I mentioned, I feel like I could actually use the shellcode location, but I figured I'd use one of those magic values, 31337 0C, to show you that PC, which is similar to, is the same as EIP or IPs, is going to contain our new value. So that would be kind of the similar way of like, oh look, it's 41, 41, 41, 41. Yeah, great. So another key thing is, I'm not sure everybody knows, if you're not familiar with PPC or any other type of RISC architecture, but it's got to be 4-byte aligned. So I couldn't do something like dead beef. I couldn't do Cafe Babe. I couldn't do some of the, Xerox 41 because they're not 4-byte aligned, and it's going to look kind of goofy. So I made sure that this was 4-byte aligned and made it happen. So we'll keep going here. So our environment contains the same size. Whoop, that happened fast. Our environment contains the same size, which is our location. Let's see. No, I'm sorry. Yeah, that's right. And then we'll // Everybody loves a // and run it. Bam. So 31337 0C, which obviously is an invalid address and doesn't exist, and that's why GDB is complaining. Just kidding. I love it when speakers require the applause because apparently I'm putting everybody to sleep. So a few other tips. Actually, I'm going to read my hand because I wrote some stuff. I had jokes that I was going to add. Oh, here's one. Does Caesar still live here? I can't find his room. Oh, yeah, that's it. Dang it. So a few fun little tips that'll help when you're actually going through the process of hunting for 0 day on the heap. I didn't know this until I read Litchfield's paper, but there are actually a few environment variables that we can utilize that will allow us to kind of have a better understanding of what's going on. And by having a better understanding of what's going on and changing some stuff, we actually get a lot of great debugging output, which everybody loves debugging output because, they provided it for us, right? One of them, so this actually used to be a bug. When Litchfield started using this, he realized, oh, by the way, it'll overwrite anything you want, and it just so happens to give special permissions. So you could corrupt all sorts of fun files with heap output. So for example, if you read a set UID binary with this environment variable, it's going to, excuse my terminology, crap out a bunch of debugging information. So if you overwrote a password file or something in security or what have you, so if you could control it, that'd be even better. But So, and AIX, the IBM AIX guys were like, oh crap, well, we didn't think about dropping perms on that because that doesn't really make sense. Oops. So I kind of thought that was funny as a side note because it had asterisks next to it in his paper. He's like, oh, by the way, somebody failed. Fail. Another thing that it does, so the heap actually grows towards the stack and it's, all contiguous and all that stuff. When you change this, the heap grows towards null. So when that occurs, you're going to anger a lot of other things by doing that. So by doing this, you're going to find heap corruption a little bit easier, in my opinion, than doing it the general routine way. And once again, when you make things easy, then hey, all right. A few more additional tips. So let's talk about PowerPC for a second. Anybody heard of anything called instruction caching? I see 2 hands. Sweet. 3, 4. Sweet. So PowerPC and I guess the other RISC guys came up with this brilliant idea. Why don't we cache instructions to make it look like we're running faster? While x86 doesn't have to do this because they feel like they're natively running faster, which that's a whole other debate, right? And they feel like instruction caching will help speed things up. So when if it knows the next 4 bytes to execute without actually having to go through and read it every time, then it's going to read 4 instructions at a time. Which 4 by 4 is, I'm from Texas, I don't know math. So 4 by 4 is whatever. 16, just kidding. See, I can do it. It's going to continue to keep these 4 instructions in the cache, so it doesn't have to keep checking every time. It's going to check every 4th instruction. One of the negative parts of this is if you don't do something what's called immediate, so there's stores and loads and all that stuff, which we can compare it to x86 to help better visualize it for some people that aren't familiar with RISC and PowerPC and all that. If you add an I on the end of most of those, it makes it immediate. And if you don't do it immediately, everything may look good on paper, but the true reality of that is you're going to be knocking your head up against the wall because you're like, oh, well, this should work. Excuse me. And it actually doesn't because it didn't actually change it in the cache. It only changed it at that location. So it hasn't reread it. So you've got to actually force it to recheck that and move that immediately. There are 2 different types of caching. Instruction caching, which is going to affect your shellcode. If you're not storing things immediately in, say, registers and other locations in memory, if you're not doing it immediately, then once again, you have to wait a few more instructions for that actually to take effect. And what happens is you expect a value to be there, and oh, by the way, it's not there. Yeah, it actually checked out. It's like, no, I'll be there in a bit, but not exactly there yet. And the other one is data caching. And so data caching is not that big a deal, but same stuff basically. People way smarter than me came up with all this stuff, say, oh, well, how can we make it run even faster? And so this has kind of been around for a pretty long time. And it seems like it still holds true today that what they're doing seems to work out well for them. All right. So I actually took this blurbage from one of IBM's PowerPC pieces of documentation. So, so it's up to 2 instructions every cycle. So every 2 instructions, it's going to go back and get another. And what it does is it actually goes out, fetches it, as you can see in the documentation here, and then it'll decode it or basically interpret it and make sure, oh, this is what I'm supposed to do. And by doing that, it's actually reducing the reads in half. So you like that math? Oh, great. All right. So 4 instructions are read from the cache, and then they're placed in a temporary buffer, which is actually it's a tiny little buffer that's actually in the processor itself. And then this caching is arrays to be allowed access as little once every 4 instructions. That's what I'm trying to say. And it's significantly reducing power consumption as well. And because we're all going towards a green environment and all that stuff, and electricity costs a lot, or it seems to be costing more and more. IBM and others thought it'd be, oh, well, here's at least one more way we can kind of reduce the voltage just a little bit more in the amps and not draw as much power. Because when you compare power and some of the other risk to x86 and x86-64, you'll find that it will draw more power if, well, I mean, it's still drawing more power, let's be quite honest, but it would be even more. So they're like, well, we're doing you a favor, but not really. They didn't do enough favors. So like I said, the instruction caching is what's affected. If we're caching instructions, then our shell code is going to pretty much flop because once again, we expected something to be here. So if we're calling a function and we need certain register to have certain values, when we do the branch and they don't exist, then it's not going to run as expected, or it's going to be a previous value that you don't really control, and it's not going to work out for anyone. So with doing immediate on all your different types of assembly, then you're going to get what you actually see instead of expecting what you are supposed to see, and that doesn't actually occur. So it looks like I'm running a little fast. I was kind of excited and can't wait to get here. So I can do a dance for you. Let me do a little review. So once again, two types of methodologies here. One, I feel that I kind of had something to do with, enlightening and showing. I may or may not be the first person. I don't know, but I felt like it was important enough that if we documented and actually got it out there, then other people will know how to both utilize this in penetration and testing environments, as well as maybe it'll get IBM moving forward to catching up with some of the other operating systems. So I mentioned Solaris and the BSDs and Linux and Windows. They're all doing all these different types of things to thwart this type of attack that's been around since the 90s, early 2000s, and we are now in a new decade, and AIX is still relying on the same old algorithms. It could be that they feel like it's hardened and trusted and they know it works and they're done with it and they're working on other projects. It could be that they feel like if by doing these sorts of things, maybe execution takes longer and maybe they're concerned about that. I don't know. Or maybe they just want it to be the old dinosaur and they're not looking forward in the future. But I do have some confidence that at some point in time, IBM is going to look back at this and go, yeah, we need to fix this just a little. So it's probably going to be like 6 lines of code to actually change, and I can't really envision that being too much of a pain. But I made that up, right? But as a developer, I kind of imagine the 6 lines that I would use, and then wham bam, there it is. So by the time I get off this podium, they may have already fixed this. I don't know. So once again, my name is Tim Shelton. I'm the Senior Vice President in Research and Development for a company called Hawk Network Defense. Once again, we're a SIM provider, and if you're interested in that, we can talk later. But so we do fun stuff, and I also like to play with iSeries. And because we work with an IBM Premier partner, that's what allowed me to have access to these types of machines, where I probably in my day job, if the rest of it, probably wouldn't have access to, because we deal with just a lot of x86 and maybe a little Mac. And so, all right, I guess we're going to go to questions because I saw a hand come up. Hopefully it's not a troll question. Go ahead. Oh.
So what's the most accessible if somebody wanted to get a hold of somebody who run modern AIX, like modern AIX?
Yeah, can you get the mic to him because I can hardly hear you. Sorry.
Sorry, the question was, what would be the most accessible AIX box that you could get a hold of off of, like, say, an eBay or a Surplus that would run the modern version of AIX?
I kind of think the answer is no. No,
it's not. That's not the answer.
I know. It's not the right answer, but it's the one I'm thinking of. So I was actually recently given an RS6000 machine, and these older machines will only run up to 5.1. In some other instances, if they're really old, they won't even run that. So it seems like Power 6 and Power 7 is what everybody's headed towards, and with that, you got to buy a newer machine. You might find one pretty cheap. I can't tell you the exact model that you'd probably be looking for, but it seems that IBM's pretty proud of what they have, and they ought to be, because they're the leaders of computers in a lot of senses, so it seems. So, but
I know like the old 6000s you could get the 5 and 4 boxes. They had like some like desktop type equivalent ones that still ran the same. That's actually probably part of the reason why there's not as much.
You think so?
Code floating around. You got to get a hold of the boxes, right?
Yeah. So and that's like 90% of it. So if you're a security researcher, it doesn't take much to find something AIX. So it seems. But I think you're right. I think it's a niche that. I talked about. Oh, by the way, all these different people are running AIX. Governments and medical field, and a lot of commercial companies. So commercial enterprise are running these types of systems, but none of the security researchers have really got their hands on it. So I had a reference earlier to how Linux in the 90s was called secure because nobody looked at it. It's kind of the same thing. It seems like IBM is calling it secure, and maybe they mean secure like permission secure. I don't really know. But from an exploit development perspective, it's an absolute dinosaur. It has absolutely nothing. There's no randomization. I found that no DEP, when I was doing this, while I was storing stuff in the environment variable, which is actually on the stack, it had no problem running my shellcode. No problem at all. So we're heading towards that direction, and so we've got to figure that out at some point. So with a 4-byte overwrite, it's going to be a whole heck of a lot harder to do return-oriented programming or return-oriented exploitation, and like return to function, return to libc, things like that, than it naturally would be, because you've only got one overwrite. So you got to pick a good one. So two things independently would actually thwart this: ASLR and DEP. But then together, we're in the same environment that we always have been, where you're begging for some data leakage, so you can find a memory address somewhere that you can preload and go, oh yeah, okay, that's what I'm using. So I found in my research that's semi-rare. I mean, not really rare, but rare in the sense that when I need leakage, it's never there, or never when I'm looking for it. So, and I say never. I've never been. I mean, rarely, just rarely. So, all right. Any questions? I actually have about 5 or 6 minutes left. So, sweet. We all want to hear you.
You mentioned DB2 and Oracle and a bunch of others. How often are you seeing WAS on AIX?
WAS?
Web Sphere Application Server.
Oh, yeah. Often. I mean, very often. So Lotus and all the other stuff. I mean, so IBM technology runs in an IBM environment on IBM hardware because IBM has all the ownership to it, and they can make more of a profit on it. But also, it's tested, it's tried. When people invest in these types of environments, they're going to go, oh, well, we may as well just use IBM's web servers, IBM's this, IBM's that, because why not? We're an IBM shop, which I know it seems like that's getting a little bit rarer and rarer than it used to be because of some of the hardware becoming so cheap. It's a complete commodity nowadays. But I'd say that any of those types of applications, that's actually a good one. So if you can think of any others, I'd be happy to hear. But the major ones that I see that are pretty impacting, it typically ends up being PeopleSoft and JD Edwards and databases and databases like Oracle and DB2, and with those types of applications, that's typically where your mission critical data and mission critical stuff is going on and is being relied upon by the business side of the company, not the IT side. And so maybe WebSphere may not be as important if you're just serving up data that's public and it's just a nuisance that the stuff's down. But we talk about, you see some of these compliance issues like PCI and SOX and GOBA and HIPAA and all that, right? They're focused on, okay, where's the important data? first of it was important because you have to identify that. Where is it stored at? And then do we have the right access controls around that to ensure that it's not being snatched out by people that we don't want it to? For example, I mean, maybe I shouldn't plug that. There's a university local from where I'm from that just had a major outage, like 27,000 medical records, I'm sorry, it was medical related, but 27,000 different people got leaked. So, you know, it kind of is what it is. You got to find exactly where the right data is, and that's why I brought those up. But maybe people saw, I'm sorry, maybe WebSphere is communicating with something on the other end that holds that type of information, and you know, maybe it's necessary to do that. But I'd say it's pretty common in older environments and starting to get rarer and rarer because A, it's a behemoth, and B, it just takes a lot to manage and maintain. So, any questions? Anything else? Great. All right. Thanks, guys.